Okay, it's Brian. This is the set of slides that I was thinking to do in class on Monday before we had our snow day. And so I'm going to ask you to watch this set of slides and then answer a quiz based on it that I will post as a Canvas quiz. And the grade on the quiz will be in lieu of this week's recitation quiz. So in lieu of your normal recitation time, go ahead and watch this video, answer the questions on Canvas, and that will keep us up to speed with the material of the class. So this is the week when we start talking about magnetic fields and forces, okay? And I'm just going to jump right in. And before we start, actually I want to tell you a guiding principle going forward. I want you to focus on the concepts first and then the equations second. Okay, when you're solving problems, you want to know the physics, like what physics is involved here, what is happening conceptually. And to be able, if you know that, it makes solving the problems easier. Folks have taken to solving problems using a shortcut, where basically they extract relevant numbers from the problem, and then they're just kind of finding an equation that those numbers fit in. That is not the way we want to solve problems. And I want you to develop a deeper problem-solving strategy. And I'm going to talk about this in some detail about what we're looking for on the homework, and also what we'll be looking for on future tests. Okay, and I'm going to be talking about that more. I'm always looking for applications of this material to the living world. And one of the things we're going to talk about this week is magnetic navigation. Sea turtles are capable of remarkable feats of navigation in the ocean. How do they do it? And one thing that they do is they use the Earth's magnetic field, and exactly how they do it is something which we'll talk about once we learn a little bit more about magnetic fields. Now here's the basic principles which we're going to be looking at. And I've always, at the start of every week, I give you a couple of slides that have the relevant concepts and the relevant relationships that you need in one place. So one thing we're going to look at is this. Magnetic fields, of course, come from permanent magnets like bar magnets, but they also come from currents. And we have an equation for the magnetic field from a line of current. We have one for a coil, where we're given the magnetic field in the center of the coil. And they also have one for a solenoid. Now, another piece of the puzzle is what direction is the field in. That depends on something called the right-hand rule. That is something we'll come back and talk about in a minute. The other piece we'll look at is the fact that magnetic fields exert forces on moving charges, i.e. a charge moving through space, or else a charge moving through a wire as a current. And we have relationships for those, and then we also have the right-hand rule to determine the direction. Those are some points I'll introduce later. Now remember, back when we were talking about electric dipoles, we had a problem here about imagining electric dipole in an electric field. And what happens if you have an electric dipole in an electric field is electric dipole will rotate so that it lines itself up with the field line, and then there's a net force on it, and there will be a force in the direction of increasing field strength. That's because I'm going to have forces on the two ends of the dipole, and this one is where the field is weaker, this one is where the field is stronger, and so there's a net force in the direction of the stronger field. And the same thing happens with magnetism. If I have magnetic dipoles, they will line themselves up with the magnetic field, and they'll be attracted to where the field is stronger. And that's ultimately why things stick to magnets. That's one of the things we're going to talk about this week. Now, electric dipoles will line up with an electric field. And the same is true of magnetic dipoles. And it turns out the basic unit of magnetism is a dipole. We can think of the basic unit of magnetism as basically a compass. And a compass will rotate to line itself up with the prevailing magnetic field at any particular location. Now, if you have an electric dipole, okay, an electric dipole is made up of a positive charge and a negative charge, and that makes a dipole. But there's two charges. You can separate it into just the positive charge or just the negative charge. That doesn't work for a magnetic dipole. For a magnetic dipole, like a bar magnet, I've got a north pole, I've got a south pole. That's two poles. That's why it's a dipole. You can't cut it into a smaller unit. If you take a bar magnet and you cut it in half, what you end up getting is two smaller pieces, each of which has a south pole and a north pole. You get two smaller bar magnets. The smallest unit of magnetism is a dipole. And one way to see that is to look at a current, is to look at the field lines. Now for this bar magnet here, I got a north pole, I got a south pole. The magnetic field lines come out of the north pole and they loop around and go back into the south pole. Okay, that's the meaning of the two poles. Field lines come out of the north pole, they go into the south pole. If I look at this loop over here, the loop of current, okay, makes the same overall field structure as a bar magnet. I get field lines that come out of one side of the loop and go in the other. And basically, one side of the loop is going to be looking like a north pole, and the other side of the loop is going to be looking like a south pole, and field lines go out of the north pole, loop around, and go back into the south pole. But you can see you can't take this loop and cut it in half. The north side is the top of the loop. The south pole is the bottom of the loop. You can't have a loop with just a bottom or just a top. You can't do that. And so that's the smallest unit that we're going to have is the dipole. Field lines come out of one pole, which is basically the top, and they go into the south pole, which is basically the bottom. And when we talk about loops, and we're looking at the forces on loops, we're often going to think about that. So if I have a loop of current, and the current's going in this direction, the magnetic field lines will be directed as you see. And they're coming out of this side, which we call the north pole, and they're going into this side, which we call the south pole. And we can assign a pole structure to a loop of current. Now, one thing we're going to be very interested in this section of the course is the magnetic field of the Earth. The magnetic field lines of the Earth point towards a magnetic pole that's up here in northern Canada. And so my compasses will rotate and they will line themselves up with the magnetic field of the Earth, like so. They're going to point north, okay? And they point towards this magnetic pole up here, okay? And that's something that we'll have more to say about later. Now, if I have a bar magnet, or else I have a loop of current, I can associate a dipole moment with it, just like we saw with electric dipoles. We could associate a dipole moment. And I associate a little arrow here. And the little arrow basically lines up with the field. If the field line comes out of one side into the other, field lines loop around like so. I'm going to draw a dipole moment that corresponds to the overall direction of the field. And if I have a dipole moment associated with a loop or associated with a bar magnet, etc., it will rotate so that it lines itself up with the field. And the magnitude of the dipole moment I represent by the symbol mu, and I bring that up for this reason. If you have a dipole and I have a field, if the dipole is lined up with the field, like this situation here, that's lower energy than if it's lined up opposite the field right here. And so you can have different possible energy states. Dipole lined up with the field, the energy is negative mu times b. Dipole lined up opposite the field is positive mu times b. And so there's a difference in the two energy states right here between having a dipole lined up with the field or dipole lined up opposite the field. Now let's look at the magnetic field of the Earth. We've said that the magnetic field lines point towards the Earth's north pole, okay? So, and actually magnetic field lines come out of the Earth's south pole. They loop around and they go into the Earth's north pole. So here's the thing. The Earth's north geographic pole, i.e. where Santa lives, is actually a south magnetic pole because the field lines are going into it. Whereas the Earth's south geographic pole, which I call the penguin pole because that's where penguins live, is where the field lines come out of. And that is the distinction which you'll need to have in mind when you solve at least one of these homework problems that we're going to be doing. Now, another thing that you can note is that the field lines don't go straight into the Earth. As you can see, it kind of strikes at an angle. And the angle that it strikes at is called the dip angle. And that is something that will be important to us as well. Now, one creature that absolutely used the Earth's magnetic field to navigate is Magnetotactic Bacteria. And here's a micrograph of this Magnetotactic Bacteria. And you can see it's got all these little pieces of magnetite in it. And basically, the bacteria itself works like a compass. And the compass will rotate and line itself up with the Earth's magnetic field. And it does that because if you look at where how the magnetic field strikes the surface of the Earth, it's got a component that goes parallel to the surface of the Earth, but it's also got a component that goes vertical. And where we are, the Earth's magnetic field is dipped at an angle of about 60 degrees below the horizontal, and so it points more down than it does north. And so these magnetotactic bacteria will actually line themselves up with the magnetic field of the Earth, and they basically just move along a magnetic field line. And that is how they tell up from down. If they want to go where the water is oxygen rich, they go towards the surface. If they want to go to where it's oxygen poor, they go for the depths. And the way that they tell up from down is not by having like one side of them be heavier. You might say, oh, one side is heavier because it's weighted with iron. That's not true. The way they know up from down is because they use the Earth's magnetic field to line them up, and it lines them up along this 60-degree angle here. This line at 60-degree dip angle, and that is got a pretty good vertical component. And now let's consider the energetics of the bacterium. Okay, so typical bacterium, this is a typical mass, this is a typical length. If we just say, hey, let's weight one end with iron, so one end is heavy and one end is light, what is the difference in energy between having the heavy end up and the heavy end down? The difference in energy is about 5 times 10 to the negative 24th joules. But there's a thermal energy scale, which is just the energy scale of atoms moving and jostling around, and that is about 4 times 10 to the negative 21st joules. So this energy is smaller by a factor of 1,000. So it's 1,000 times smaller. And so it turns out that the difference between heavy end up and heavy end down is much, much less than the thermal energy scale. The bacterium won't float heavy end up or heavy end down. It's being jostled too much for that to ever work. But what will work is lining up with the Earth's magnetic field. So I want you to compute what is the difference in the energy level between being aligned with the field and aligned opposite the field for this magnetic moment and this magnetic field. And we want to compute a difference in energy, and we can compare that to the thermal energy scale. And I want you to pause the video right here and do a quick computation, because in class I would say I want you to work with your neighbors, I want you to do this calculation. You're not going to work with your neighbors, but I want you to pause the video right here, complete that calculation, and then we'll come back. And if you compute the difference in energy between being aligned with the field, which is negative mu times b, and aligned opposite the field, which is positive mu times b, you get a difference in energy of 1 times 10 to the negative 19th joules. That's significantly greater than the thermal energy scale, and it's bigger by a factor of 100,000 than the energy scale of heavy end up or heavy end down. And so heavy end up, heavy end down doesn't make any difference for bacteria, but lining up with the magnetic field does work. And so they're just little bar magnets. They line up with the field, and then they just scoot up and down along the magnetic field lines. Now, you know that magnetic fields come from permanent magnets. You've seen that before. Magnetic fields are also produced by currents, and in particular current loops. And another thing that makes magnetic fields is an atomic scale. Electrons, protons, nuclei, atoms will have a dipole moment associated with them. They will produce magnetic fields as well. And all three of those things will be important to us. Now here's a relationship for the field of a current-carrying wire. Okay, so if you take a wire and you put a current through it, as in this picture right here, okay, there are going to be magnetic field lines that go in circles around the wire. Okay, so they're going in circles around the wire. And you can see these compasses are lining themselves up in a circle, like so. The magnitude of the magnetic field a distance r away from the wire is given by this expression right here. And mu 0 is a constant that has this value right here. Current is in amps. R is the distance from the wire. And the unit for magnetic field is the Tesla. Okay? But here's the thing, the magnetic field could glow in one direction or it could go in the other direction. What determines whether it goes clockwise or counterclockwise is the sense of the current. And the way you determine the direction that the magnetic field lines go is this. You imagine taking your hand and wrapping it around the wire so that your thumb points in the direction of the current. And so then, therefore, your fingers curl around the wire in the direction of the magnetic field. That's the sense in which they curl around the wire. And I have a little video that I'll show when we're back in person. But now I want to talk about some notation. We are going to be looking at things which are wickedly three-dimensional, so we have to have ways to represent three-dimensional things on a two-dimensional page. If I have a vector going into the page, I draw it this way. If I have a vector coming out of the page, I draw it this way. If I have a current into the page, it looks like this. Current out of the page looks like this. Okay, that's going to be an important thing for us. Now, if you have a loop of current, okay, the loop of current, the magnetic field in the center, and that's the only place where we can exactly calculate it, dead in the center of the loop, it's mu0, which is the constant we've seen before, times the number of loops of current that you have stacked up, times the current in the loops, divided by 2 times r, where r is the radius of the loop. And the sense of it we determine by using the right-hand rule. You wrap your hand around one part of the coil so that your thumb is pointing in the direction of the current, and then the sense in which your fingers curl, okay, is the sense of the magnetic field. So in this case, it's coming in the left side and it's going out the right side, okay? And there's a couple of handy diagrams in the textbook that you can look at that kind of show you how this works. Now, we've seen how you can use electrodes to determine the electric dipole moment of a person's heart, but it turns out you can actually model a person's heart as working like a loop of current. As you have a wave of depolarization sweep across the heart, there's actually currents that move, and it looks like a loop of current. And so as a consequence, you end up producing a magnetic field as well. So it's possible to do a Magneto Cardiogram. And here's a Magneto Cardiogram of someone's heart, and the heart is working like a loop of current somewhere in here. And so you end up having places where the magnetic field is coming out, and I have places where the magnetic field is going in. And so you can actually tell substantive things about a person's heart by measuring not the electric field, but the magnetic field. One last source of magnetic field we'll look at is the solenoid. Now, a solenoid looks like a coil, except I've just got a lot of loops, but I stack them up so that they have some length. And that's kind of like a slinky. And the magnetic field inside a solenoid is given by this relationship right here. It's mu0 times n times I. N is the number of turns, I is the current, and then divided by L, where L is the length. And the field is large and uniform inside and essentially zero outside. That is a proposition you'll be able to test when you measure the field from a solenoid in the lab. Now let's do a quick assessment to see how you're feeling about the right-hand rule. So suppose I have magnetic field produced by a current in this wire, and it's directed like so. And so I've got X's and I've got dots, and that tells me something about the sense of the field. The question is, what is the direction of the current? Is it towards the top of your screen, or is it towards the bottom of your screen? Which one is it? This is the first question that I'll ask you to consider in the quiz that's posted, and that'll be posted as a quiz, and the grade on the quiz will go in for your recitation. So go ahead and look at question number 1 on the quiz. That's this question right here. All right, next check. Suppose I have 4 wires that are carrying a current, like so. All of them have a current to the right. And on top of each wire, I set a compass. One of these positions of the compass is correct, the others are not. Which one of these compasses is in the correct orientation given the magnetic field that will be produced by the current in the wire? And you're imagining these as 4 separate situations separated by a great distance. So it's just one compass and one wire. In which case is the compass oriented correctly? Is it A, B, C, or D? This is going to be question number 2. on the quiz that I will post. Now suppose I have a loop of current, and think the way we've drawn this is comparable to how we've drawn diagrams in the textbook. Okay, so I have a loop of current, and you're looking at a cross-section of it, and the current direction at the top and the bottom is given. Given that, what can you say about the direction of the magnetic field at this point, which is exactly in the center of the loop? Will it be A or B or C or D? This is question number 3 on the quiz that you have. Now we're going to turn to the force on a moving charged particle. Okay, if you have a charged particle of charge Q moving at a speed v in a magnetic field B, the magnitude of the force is Q times V times B, and it's times the sine of alpha. But in fact, we're going to be looking at situations where alpha is basically equal to 90 degrees, so the sine of alpha is equal to 1. Alpha is the angle between B and V, and we'll typically work with situations where that's 90 degrees. The magnitude of the force is Q times V times B. The direction of the force is given by the right-hand rule. If you take your hand and you put it in this orientation, your index finger points in the direction of the velocity. Your thumb points in the direction of the velocity, your index finger points in the direction of the magnetic field, and your middle finger points in the direction of the force. And so I end up with those 3 perpendicular directions. You've made a little right-hand coordinate system. And here's a picture of me making a little right-hand coordinate system, and I've got this little device that I use for it as well, and I'll show you that when we get together in class. And this is going to be kind of a gang sign for us, and this is something that I will explain more about later. But you take your right hand, your thumb is the direction of the velocity, your index finger is the direction of the magnetic field, and your middle finger is the direction of the force. Okay? So let's do a quick check. If I have a positively charged particle coming into a region where the field is directed like so, what will be the initial direction of the deflection? Okay, will it go, could go up, could go down, could come out of the page, could go into the page. Which will it be? And then how about for a negatively charged particle? Which way will it go? Again, could be left, could be right, could be in, could be out. We want you to think about that. This is going to be question number 4 on the quiz that you'll see. Now, magnetic fields exert forces on currents, and so magnetic fields will exert forces on currents in wires. And the magnitude of the force on the current is just I times L times B. Alpha is the angle between the current and the magnetic field. We're typically going to work with situations where that's 90 degrees. And the direction of the force is given by the right-hand rule. The direction of your thumb is in the direction of the motion of the positively charged particles, but that is the same as current. So your thumb is in the direction of the current, your index finger is in the direction of the magnetic field, and so your middle finger will be in the direction of the force, and so we can use that. Now let's do a quick check. Suppose I have a current in this wire that's directed towards the left side of the screen. Magnetic field as shown here. Question, what is the direction of the force on the current? Towards the top of the screen, towards the right, towards the bottom of the screen, or toward the left? This is going to be question number 5 on the quiz that you will have. Next up, if I have a coil of wire carrying a current like this, and it's in a magnetic field, question, which way will it rotate? Okay, so think about the forces on the different parts of the loop. Will it rotate clockwise? Will it rotate counterclockwise? This will be question number 6 on your quiz. And finally, we're going to look at a problem which has some numbers in it. Okay, some people are worried about the magnetic fields generated by electric currents in transmission lines. And we just want to get a sense for how big are those magnetic fields. So here's the question. What is the magnetic field on the ground below a high voltage transmission line 20 meters above the ground that carries a current of 200 amps? And the next question is, what fraction of the Earth's field is this? Now, the first thing we're going to do, of course, is to strategize. In my strategize step, I'm going to say, I am going to be computing the magnetic field from a line of current. okay, because it's a transmission line. So it's a big wire carrying a current in a single direction. So I'm looking at the magnetic field from a current carrying wire. Next piece, I'm going to prepare. And for my prepare step, what I'm going to do is I'm going to draw a picture. And I'm going to draw a side view. So here's the ground. And here's my wire, some distance above the ground, and it's carrying a current. And I'm going to take the current and have it be into the screen here. So current's going like that. When I have a current into the screen, I'm going to get circles of magnetic field that are directed this way. And I use the right-hand rule to determine the sense of the current. So on the ground, the magnetic field lines are going to be going parallel to the ground. And if I'm on the ground, the distance I am from the wire is just equal to the height of the wire above the ground, which is 20 meters. And the current in the wire is 200 amps. And so that's a fine preparation. Once I've got that, I can go ahead and put numbers in the equation. And if I do that and solve, what I get is this. I get a magnetic field that's about 2 microteslas. And then we can use to answer question B, what fraction of the Earth's field is this? That's about 4% of the Earth's field. And my assessment is this, is to say, like, I haven't seen a lot about this. And it says here, although the evidence is weak, there's been some concern. So it's not saying it's a huge deal. And so I'm expecting the field to be relatively small in this result, given the overall tone of the passage. And so my assessment is, I expect a small result. That is, in fact, what I see. And so that gives me confidence in my calculation. Now, one of the things that we'll talk about is magnetic navigation. And it turns out hammerhead sharks are fantastic at magnetic navigation, and how they do it is something we'll talk about in some detail when we talk about chapter 25. But first, I want to look at the results of a very particular study. If you want to prove that sharks can navigate using the Earth's magnetic field, you have to prove they can, in fact, detect magnetic fields. And how do you do that? An investigator took hammerhead sharks and put them in a tank, and the sharks were trained that they would get a food reward when a field was present. And the field was generated by a current of 1.5 amps in a 100-turn coil of wire that was wrapped around a tank that was 7.5 meters in diameter. And then they had trained the sharks that when a field was present, they'd get a food reward. Then they would switch on the current in the tank, and the sharks would head for the center of the tank, where there was a little hatch that would dispense a food reward. And so they were clearly detecting the presence of a field. So here's the question. How big was the field? And how large was that field compared to the field of the Earth? Is it smaller or is it larger? Okay, that's what we want to do. Now, the first piece is to strategize. Okay, and so I'm going to strategize, and I'm going to say, I am calculating the field from a coil. I've got a multiple turn coil of wire wrapped around the shark tank. And so I'm looking at the field from a coil of wire, and I'm looking at the magnetic field in the center of the coil. That's my strategize. For my prepare step, what I would do is I would sketch the situation. So if I have a top view of my situation, there's my tank. I have a coil of wire that gets wrapped around the tank, like so. And I've got 100 turns of wire, so N is equal to 100. And it's carrying a current of 1.5 amps. And I'm looking for the magnetic field directly in the center. Now, if the current goes in this direction, another thing I'll do just to get myself practice is I'm going to go ahead and calculate the direction of the field. The direction of the field inside here is going to be into the screen. And I can compute the magnitude right in the center because we have a relationship for making such a calculation. And I want you to go ahead and complete that calculation and see what you get for the strength of the field in the center of the tank. And then answer the question, is this field larger or smaller than the field of the Earth? That is going to be question number 7 on the quiz, which you'll take as part of in lieu of recitation this week. And I'll give you a hint for the assessment. It's smaller than the Earth's field because the point was to show that the sharks could in fact detect a field on the size of the Earth's field, and exactly why that's important to them is something that we'll talk about later. And that's where we're going to leave it until we come back on Wednesday. And Wednesday we'll have an in-person lecture and lecture over Zoom, and we will talk about the motion of charged particles in a magnetic field. I hope you folks are staying safe and warm on this snowy Monday, and I look forward to seeing you in person soon.